Alrighty, let's go ahead and learn about natural logs. That is this button right here, the LN. So natural logs. They have the same properties just like regular logs. Inverse property, remember e to the natural log of x is equal to x because they cancel out. Just remember like 3 to the log base 3 of x. The 3 and the log base 3 cancel out and you're left with the x. Same thing here. The natural log of e to the x power, these actually cancel out and you're left with the exponent there. Also the natural log of e, when you have the ln and the e next to each other, they equal 1. Now we have this, example 1a, e to the natural log of p. So what is that equal to when we simplify it? The e, the natural log, whenever you see those next to each other, they cancel out and you're just left with the p. Not to the power of p and not 1 to the power. 1 to the p power, it's just p. Here, natural log of e is equal, or natural log of e to the 3c squared plus 1 power. These cancel out, and you're left with the number right there, the exponent. 3c squared plus 1. The three different properties of natural log, again, this is exactly like the same as logarithms. I call it expanding and despanding. Expanding when they say find the sum and difference, meaning they want to make it bigger. So they want more terms to it. If they want it to simplify into one logarithm, that means they want to despand it and they want to make everything in just one log. To do that, these go hand in hand. If you see two things multiplying, that means you can separate them in terms of adding. So when they're multiplying, they're adding. So the natural log of xy, it'll be the natural log of x plus the natural log of y. The natural log of a over b, when they're dividing, they are separated by the subtraction sign. And then the natural log of a to the p power, whenever you have an exponent, you move that exponent up here and now it becomes a number up there. So these also go hand in hand. When you're adding, you can put them together into one logarithm by multiplying. When they're subtracting, you can put them together by your first one divided by your second one. And here, if you have a number in front of the natural log, you can make that your exponent. So they go hand in hand, just like the logarithms. Example 2, here they said to put it in terms of sums or difference, meaning they want you to expand the expression. There's one natural log there. They want you to expand it as much as you can. Expand it to as much terms as you can. You have the natural log of 6e. 6 and e, they are multiplying, so you can apply the first rule. So I'm going to put number 1. And that means you can put them in additional terms. So natural log of 6 plus natural log of e. Now, we want to simplify as much as we can. Natural log of e, just like up here, whenever we see that, that means it equals 1. So natural log of e cancels out and turns into 1, just doesn't disappear. Here, b. Here, there's a couple things going on. You have to see the bigger picture. Here, we have, yes, they're multiplying, but the main factor is that they're dividing. It's dividing the numerator by the denominator. So that means we apply the second one. So it's numerator, 3e, divided by, so that means you subtract the denominator. So 3e divided by x, same thing as 3e minus natural log of 3e minus natural log of x. Now, we're not done yet. We have natural log of 3e. Those two numbers are right next to each other. That indicates that they are multiplying. We have to apply this property to it. We're trying to expand it as much as we can. Now we get the natural log of e plus natural log of 3 plus a natural log of e. This turns into that. And then bring that down, natural log of x. We're not done yet. Whenever you see the natural log of e, you have to simplify that because now that turns into 1. Your answer is natural log of 3 plus 1 minus natural log of x. Or how the book has it, the natural log of 3 minus log of x plus 1, where my finger is. You can do it that way. I honestly don't care. It means the same thing. C, the natural log of e to the 5x squared power. If we go back to the original rule of inverse properties, whenever you have the natural log and the e right next to each other, they cancel out and you're just left with the exponent. That was easy. Last one. This is where a lot of things is going on. If you see up there, they are multiplying, it's dividing, and we have a power. So we have three things going on. But now we have to focus on the main thing. Yes, they are dividing, but now this square is being applied to the whole fraction. We have to apply the rule, the third rule to it. meaning your exponent now becomes a number in front of all that logarithm. You end up with 2 natural log of 2x cubed over 3, or e to the 4th power. Next thing is we have a fraction. When you have a fraction, you have to think of subtraction. So now we have, again, you have that 2, you have to keep that 2 in front. You have the 2 times the natural log of your numerator, 2x cubed, minus your denominator. Your denominator is, I'm going to put parentheses here, natural log of e to the 4th power. So this 2 is being applied to everything here. I'm just going to put parentheses here and not worry about this 2 now. Now you have 2 times the natural log of 2x cubed minus the natural log of e to the 4th power. We simplify even more. Here, 2x cubed, that means they are multiplied. We can go ahead and simplify that there. So again, the 2 is on the outside. You want to leave that 2 on the outside. We have the natural log of the first term plus natural log of the second term. Now, we have this last one is the natural log of e, actually, let's go ahead and simplify here. The natural log of e to the 4th power, if you see it, the natural log is next to it and you get the 4 by itself. And that's what you want. You want to simplify as much as you can in this case. So here we expanded even more. Here we applied the inverse property, meaning if you have natural log and e next to each other, you're just left with the exponent. And now, before we apply the 2, because we do have to apply the 2 to everything, but before we do, want to see if you can simplify everything here. Here is just 2. Here you have x cubed. You have an exponent. You can simplify this exponent. Your exponent now becomes the number in front of your whole logarithm. And you're left with that. Now, everything is simplified as I can get in between the parentheses. Now you can go ahead and distribute this 2 here, but make sure you do that in the very last step. Now when you do, remember, this number is now multiplying into your factor. It's multiplying into your number in front. So natural log of 2, there's no number there. It's like a 1. So 2 times 1, you end up with 2 natural log of 2. You're not multiplying the 2 numbers there. Now we have 2 times 2 times 3 times natural log of x, a lot to say. So now 2 times 3, you can multiply them. You get 6 natural log of x. Because the number is in front of the natural log, you can go ahead and multiply them. And this is a whole number, so you can go ahead and multiply it and you get minus a. And that will be your answer. I would say the tricky part is just be careful of the 2 and 2. You automatically think, I'm going to make it 4. Nope. It has to be the number in front of the log. And this will be your answer here in simplified form. You could leave it like this. I'll accept both. Just make sure you have it correctly written down. The last part is, this is where science is applied to this. You have the natural base functions. They use this a lot with experiments. You have the growth, the decay, and where n of 0 is. In your book, this will be page 567, it talks about thallium. Thallium is a radioactive substance that can be injected into the blood as part of a health test for the heart. Then it's tracked through the bloodstream by a special camera. Thallium has half-life of 73.1 hours. How long will it take for 1 gram of thallium to decay to 0.1 gram? So we have to go ahead and choose one of those 3 formulas to use, and then obviously we're going to use decay 1. So here we're trying to see how much it's going to decay. We have to first find what our K is. I have everything written down here. We're using the decay equation. We have n of t being 0.5. We're going to start with the half-life and full life. So n of t, their starting point, is half-life. Our n of 0 is the full life of it. We have t being the number of hours, which is 73.1, and then k being thalliums. If you really understand the question, it's asking you, how long will it take? They want to find how long in total. We can't just say, oh, it's 73.1 hours. That's not correct. We have to see how long it's going to decay from 0.1 to 1. Now here, we have to find what the k is in this function here. When I go ahead and plug everything in, I get 0.5 is equal to 1, that's the n of 0, n sub 0, e to the negative k times t power, which is 73.1. So 0.5 for n of t. We have our 1 because it's our n of 0. And we have e to the negative k, which we don't have, we're going to find that k first, the constant, times the t, which is 73.1 hours. So now we go ahead and find them. In this case here, you have to take the log of each side. In this case, we're taking the natural log of both sides. And this is very important whenever you're solving for something. So now we have the natural log of 0.5 is equal to the natural log of e to the negative k times 73.1. We take the natural log of both sides. Natural log of 0.5 just becomes the natural log of 0.5. We're not going to solve it out just yet. If you notice here, the natural log of e, whenever you have those two next to each other, they cancel out, and that's why we take the natural log of both sides. We end up with negative k times 73.5, or 73.1, we get negative 73.1. And now, okay, forgot that. Now we have to solve for k. We divide both sides by negative 73.1. And we end up with k being equal to 0.00948. Take the log of both sides. Then after that, you find your constant. Now, remember, we're asking for how long will it take. So now we're dealing with how long will it take. So t equals, I would say just a question mark because we're looking for that. Our constant is what we found from the beginning, is 0.00948. Now our n of t, we're dealing with the actual grams. How long would it take for 1 gram of thallium to, to move to decay at 0.1? So it's starting from 1 and we want it to decay from 0.1. So that's why we have 0.1 ending, but we're starting with that 1. We go ahead and use the same formula up here. N of t, that is 0.1, is equal to n sub o times e to the negative k, and k is 0.00948 times t, which we don't have because we want to see how long it will take. First thing, you take the log. In this case, if you see an e, you always think of natural log. If you see an x, you think of the regular log. So you take a natural log of both sides. You have the natural log of 0.1 is equal to the natural log. There's that 1 there, but remember that 1 is just understood. So the natural log of e to the negative 0.00948 t power. And now we remember that the natural log of e, when they're right next to each other, they cancel out. So you're left with the exponent. So natural log of 0.1 is equal to negative 0.00948 t. Now we can get the t by itself. Divide both sides by this number. I'm just going to put an arrow there. It's too much work to write down. Natural log of 0.1 divided by negative 0.00948. You end up with, I think I didn't write it down. But when you divide it, you get 242.9. 242.9 hours. That's how long it's going to decay. All right, if you need any more help, make sure you go ahead and email me. Keep doing your homework, and miss you guys.